So today we're going to be going over shear and moment diagrams, but this time with distributed loading. And there are a couple relationships that you need to know. So for example, let's say you have a situation such as this example here. So for this problem statement, we have draw the shear and moment diagrams for the beam. Now the only difference when it comes to the previous problems we dealt with for the shear and moment diagrams is this one includes a distributed load here. And this one specifically is being held by a cable here from point C. We have a force pulling it downward 500 newtons at point B. We have point A and C, and we have the necessary dimensions here. So a couple relationships that you need to know for this is the change in shear and the change in moment. So there are two equations for this, which are the change in shear is equal to the integral of Wx dx. I remember Wx is just the load that we have. In this case, it would be constant 250 newtons per meter. And remember, the change in shear is nothing more than the shear at point 2 minus the shear at point 1. And these are arbitrary locations. So in this case, point 1 could be point A, and point 2 would be the next point, which is point B. Now the change in moment is equivalent to the integral of the shear with respect to x. And now once I'm drawing the shear and moment diagrams, this will be a lot more simpler. But essentially the change in shear is the area under the loading curve, Wx, and the change in moment is the area under the shear curve that we're going to be drawing. So the change in moment, m2 minus m1. And these are the equations we're going to be using to solve for the moments at the point 2 here. So the first step, like always, is basically since we have a distributed load, you find your resultant force with the appropriate location of that resultant force. Remember x bar, going back to the previous video. And once you found the resultant force and its location, you solve for the appropriate reaction. So we have a hinge here, we have an x and y direction. Now for this cable, instead of trying to get the resultant forces here, the reaction forces, you basically just have a force along the cable, this, and let's call this FC. Now remember, since we do have the dimensions of this cable, we actually have the slope, the rise and the run. So the run is 4 meters, the rise is 3, and from there you could get your slope, which is 5 here. And we're going to be using this to find the components in the x and y direction of FC. So of course you apply your static equilibrium equations, and then you find your FC and your reaction forces. So I'll go ahead and just skip to the results of these. But I encourage you guys to practice on your own to see if you get the same results. So finally, after doing the sum of moments, sum of forces, and x, we get our reactions. AX is equal 500 newtons and AY is equal 625 newtons, and FC, the tension in the cable FC, is equal to 625 newtons. Now let's go ahead and start drawing the shear and moment diagrams with all these reaction forces. So I went ahead and redrew the beam here with the reaction forces and all the distributed loads and so forth. And then I went ahead and drew the diagrams for the shear and the moment, which we're going to be drawing here soon enough. So first off, we see the reaction force AY 625 newtons, which means our shear is going up 625 newtons. So let's plot it here, 625. We already know the units in newtons here. Now, how would we get the shear at this point? This is B, this is C, and this is A. Remember, we go back to the relationship that I initially gave, the equation, which is the change in shear is equal to V2 minus V1 is equal to the integral of Wx dx. And Wx is the load curve that we have here. So we have V1, which is 625. So all we need to do is solve for V2 here. Let's go ahead and write that. So we have V2 take away V1, which is 625 newtons, is equal to the area under this load curve here. So the integral from 0 to 2 meters, right, because that's the location where that distributed load is being applied to, which is 250 newtons per meter. Now, since this is constant, there we have no variable x in this integral, so it's 250 newton per meter, which is just a constant with respect to x. Now, taking the integral of this, of a constant, would just be that constant multiplied by x. And of course, then you integrate and you solve for the integral from 0 to meters. So you see 250x is the integral from 0 to 2, which is 250 newtons per meter times 2 meters. It's always a good idea to keep the units just so you won't get confused. But once you've had enough practice, you kind of understand all the unit cancellations and so forth. So now we have V2 being equal to 125 newtons. Now, one thing I forgot to mention was I left out the sign convention. So since the load is in the going downward, it's going to be negative, negative, and it's going to be a negative. So our V2 is 125. So it'll be somewhere around here, 125. And from here, so since the distributed load is constant, that means the relationship of the shear is going to be linear. So you just connect it with a straight line here. So you have 125, but at this point you have another 500 newtons going downward. So it's going to be 125 minus 500, which gives us negative 375 newtons of shear. And then from here, since we don't have any distributed loading, then this means this internal shear is going to be constant throughout this section of the beam itself. So it's going to be just a straight line over here, which is still negative 375, but we still have FC. We take the only the y component going upwards, and if you do your trig here, we see that's going up 375. So it's going to be 0 here. So this is our shear diagram. Now we're going to go ahead and do the moment diagram, which we're going to be using that relationship that we had, which is the change in moment is equal to m2 minus m1, which is the equal to the integral of the shear with respect to x. So in other words, the integral of the shear force with respect to dx is the area under this shear diagram that we just did. So the change in moment is equivalent to the area under these curves here. So for the moment at point A exactly, we have no moment here. Only until we start going into the beam itself where there's loads and such will we start getting a moment. Um, the easiest way is if your reaction does not have a reactionary moment, then that means your initial point for the moment is going to be 0. Remember, there are some supports that have a internal moment, but in this instance, we have a hinge, so we only have forces in the x and y directions, but not a reactionary moment in this case. So that's the reason why we have 0 moment in the beginning here. Now, the area under this curve is going to be m2 minus m1. Since we see that this is a simple geometry, you actually have a rectangle here at 125 newtons, and the other one is a triangle. So you can actually just simplify it and use the areas that we do know for rectangle and a triangle to solve for the maximum shear at this point over here. So m2 take away 0, which is m1, is equal to, we have the width or height of this rectangle here, 125 newtons. The width of it is 2 meters, so 125 times 2 meters, plus the area of this triangle, which is 1/2 base, which is 2 meters, times the height, which is 625 newtons, minus the 125 newtons. Just be careful with that. Because remember, keep in mind this triangle starts from this point to this point on top, so it's the subtraction of 625 minus 125. So M2 is 750 Newton meters. So it goes 750. So from here, we see that for the shear diagram itself, we have a linear relationship, which means the moment diagram is going to have a parabolic relationship. Now, if this is a little bit too hard for you, you could actually do the shear and moment equations, and that's exactly the relationships you're going to be able to see. You're going to see whether it's a parabolic relationship, a linear, or constant. And so that makes it a lot easier when you're barely starting out to learn this. But once you do this enough, you s- once you do this enough, you're able to visually see if the loading profile is constant, that means the shear is linear. If the shear is linear, then that means it's parabolic. Those are the kind of relationships. If there is no force, then that means it's just constant. If it's constant, then it's linear. If it's linear, it's parabolic for the following diagrams, right? The shear and the moment. Now for the second portion of it, we already see the areas 375 times 2 meters here, right? Just the area under this curve. But keep in mind, this is negative, which means we're going to have a negative moment. So from the positive 750, we're actually going to be subtracting it, going downwards, because slowly it starts decreasing. Now, since this is constant, the relationship for the moment is going to be linear. Not parabolic, but linear. So we see 375 times 2 is 750, but it's negative because it's negative below this line here, 0. So it goes downward. And this is how you do the shear and moment diagrams when it comes to distributed loading. You could use these equations to find the areas under the curve. The relationship of the change of shear is equal to the area under the loading curve, and the change in moment is equal to the area under the shear curve itself. And once you do this enough times, you're actually able to visually just do the shear and moment diagrams. You're able to get the area under this curve. So just to reiterate, remember, if you see a constant relationship, then the next relationship either for the shear or the moment is going to be linear, and if it's linear, after that is parabolic. So we see that there is no force being applied here from point B to point C. That's why we have a constant shear. And since we see the shear is constant, that means the moment is going to have a linear relationship. Now going to the load profile, since the loading was constant, that means the shear had a linear relationship, and from there the moment had a parabolic relationship. And so this is how you do it visually. You see the reaction force 625, so you go up. Then for every meter along this section, you go down 250 newtons. So 250 for first meter and another 250 for the other one. So you have 125. Then from here, if you have an external force being applied, you go down another 500 units. Then there's no forces being applied in this area. Then you go constant. And at this location, you have FC going upward, which is actually positive 375. So it cancels out and goes back to 0. And again, since we did the moment diagram was a lot simpler, the area under the curve as well, you just multiply, add them up, this, and this is how you do it. The more you practice, the easier it gets. But these relationships are the ones that you should remember, and these are the ones that you're going to be utilizing. And so this is how you do the shear and moment diagrams when it comes to having distributed loads and so forth. These two equations are going to be important to use.